Is going to be about the lesson on section 4.4 about the mean value theorem. Okay, there's some good stuff on in Calculus for Dummies to help you with this, so I encourage you to take a look if you haven't already. I know that it's kind of weird to say or to ask you to do some reading in a math class, but it will help you to try to understand some of these concepts. Okay, so the first thing I'm going to do is actually talk about something called Rolle's theorem, which is a very specific version of the mean value theorem. So essentially, what Rolle's theorem states is that if you have a function that's continuous over a closed interval, all right, so between two numbers, and it's differentiable over that interval, and here's another thing, the values of the endpoints, when you plug them into the original function, are the same, then there must be at least one value in between a and b that when you evaluate the derivative of your original function f at that value, it would be 0. All right, so that's a lot going on there. I recognize I use a lot of vocab, but hopefully you can kind of visualize and see in these different figures or these parts of the figure 4.21, you can see some ways that this must be true. Okay, so I'm going to do two applications of this Rolle's theorem. All right, so here's the first one. We're going to use Rolle's theorem and find any value c that when I plug it into the derivative of this f of x function, I would get 0. So the first thing I'm going to do, all right, is I need to make sure that my function is continuous, which this is a quadratic, so I know it's continuous everywhere, and that it's differentiable over this interval. So it also, because it is a quadratic or a polynomial, both those things are true. So it's continuous and it's differentiable over this interval, -2 to 0. All right, now the next thing is to plug in the endpoints. So evaluate f of -2 and f of 0. And if these are the same, then we can keep going with Rolle's theorem. Okay, so we have -2 squared is 4. 2 times -2 is -4. 4 plus -4 is 0. 0 squared is 0. 2 times 0 is 0. 0 plus 0 is 0. So that is a check because both of the endpoints, when you plug in their values into the f of x function, you get the same number, right? The fact that it's 0 doesn't matter. The fact that they get the same number is what's important. So now we are ready to use Rolle's theorem to find the value for c such that when I plug it into the derivative of this function, it makes 0. So let's find the derivative of this function. So d dx of x squared plus 2x, which is going to be 2x plus 2. All right. So I know that there's some value. So I'll say some value. We'll call it c. That when I plug it into this derivative, right? So I guess I should make that c as well. It gives me 0. So if I solve, 2c plus 2 equals 0, then I will find my value for c that is true for this Rolle's theorem. All right, so my value for c is -1. So we're saying if we plug c, -1, into the derivative of this function, I would get 0. So let me show you graphically what we just did with minimal calculus, mostly algebra. So I'm going to plot x squared plus 2x All right, so x squared plus 2x There we go. And we're looking at the interval between -2 and 0. So here we go. We plugged in -2, we plugged in 0 to the function, and we got 0. So that was part of our work to make sure this was actually applicable. And then you'll notice at this c value of -1, right, if I were to draw that tangent line right here, you would notice that the value for that tangent line, or the slope of it, is 0. So we're saying at that point, the derivative of this function evaluated at -1 would be 0. Okay? Now let's do another one. Same process, guys. All right, another polynomial. This time it's a cubic function. So it's still going to be continuous everywhere, and it's differentiable anywhere. So we know we're good there. Let's plug in -2 and +2. So we have -2 cubed minus 4 times -2, and 2 cubed minus 4 times 2. So -2 cubed is -8. But a -4 times a -2 is a +8. So when you add -8 and a +8, you get 0. Over here, we have 2 cubed, and then 4 times 2 is 8. 8 minus 8 is 0. Again, I don't want you to focus on the fact that they're 0. Just focus on the fact that they're the same. Okay, so let's find the derivative of this function. So d dx of x cubed minus 4x, which is going to be 3x squared minus 4. All right, so there's some value for this derivative, we'll call it c, that when I plug it in to this derivative, I would get 0. So that's 3c squared minus 4 equals 0. So I move the minus 4 over to get 4, divide by 3, and I get 4/3. So taking the square root of both sides, I get c equals 2 over the square root of 3. And I should say, since I took the square root of both sides, I should say plus or minus. Okay? If you wanted to rationalize the denominator, that would become 2 times the square root of 3 over 3. Your choice. All right? Let me show you graphically what I'm talking about here. So I'm going to plot x cubed minus 4x. X cubed minus 4x. And I want to focus on between -2 and 2. All right, so you can see our two values where the derivative would be evaluated at this value and get 0. So they have horizontal tangent lines to this curve at these values. So you notice it's a decimal, but if I were to type in my two answers, I had 2 over the square root of 3. You get the same thing. I'll do the negative version here. 2 times the square root of 3 over 3. You get the same thing. So I got my positive or negative version there, positive version here. Decimals are fine, guys. Your choice, or leave it as a fraction. All right, so this confirms with Rolle's theorem that we have actually two values for c, that when we evaluate the derivative at those values, we would get 0. Okay, so that's Rolle's theorem. Again, that's a very specific use of what is called the mean value theorem. So let me talk about the mean value theorem. So it's kind of like back it up a little bit and not to be so specific. So the mean value theorem, some of the things are the same. The function f still needs to be continuous and differentiable, just like we had before. But this time, the values for the endpoints, when you plug them into the function, they are probably not going to be the same. All right, so that was a specific piece to Rolle's theorem, which does not have to hold true for the mean value theorem to exist. This essentially says that if you have your function is continuous and differentiable over this interval, then there is at least one point c, just like we used before, that has, when we plug it in to the derivative, it has the same value of the slope, all right, for the tangent line to that curve at that value c, as the slope of the points, all right, I should say the line that connects the endpoints. It's kind of a little easier to see on the sketch here. I'll try to show you by drawing. So here are the endpoints, okay? And you can see this one is the line that connects the endpoints. And here are the values for C. I'll just do this one up here and down here, right? That have, when I draw the tangent line to those, to the curve at those points, the slopes are the same. So they have parallel, they're parallel lines, they have the same slope. So essentially, some of the stuff is going to do the same, but I'll show you graphically to kind of help after we do the calculus and the algebra. But mean value theorem states that there's at least one value c that if I were to draw the tangent line to this curve at value C, the slope of that line would be the same as the slope of the line that connects the endpoints. Okay, that was a better job of explaining it. All right, I'll do my best to kind of show you in these two example problems. Okay, so we have the parent function for the square root function, the square root of x. So you guys know what that looks like. We'll graph it as well. And we want to find it over the interval between 0 and 9. Now, if I sketch that curve, it's continuous, it's differentiable over the entire thing, so we're good there. So we need to prove or find out, using the mean value theorem, the value for C that gives us the same slope of the tangent line to the curve at that value C that's equal to the slope of the line that connects the points 0, 0, and you'll see when we plug in 9, 9, comma 3, right? Because the square root of 9 is 3. All right? So we know that it's continuous. We know it's differentiable. So the first thing I'm going to do is I'm going to find the slope of my line that connects the endpoints. Let me actually first just plug in so you know what the endpoints are. I'm going to plug in 0, plug in 9, square root of 0, square root of 9. So this is equal to 0, and this is equal to 3. So my ordered pairs are 0, 0, and 3, comma, not 3, comma 3, sorry about that, 9, comma 3. So let's find the slope of this line. So we have 3 minus 0, the change in y, over the change in x. So reduce, that gives you 1/3. So there's some point out there between 0 and 9 that when I find the tangent line to this curve at that value C, the slope of the line will also be 1/3. Right? It has to be parallel. Okay. So now what I'm going to do is I'm going to find the derivative of this function. So watch how I write it. d dx of x to the 1/2 power. Right? I want to use the power property, or the power rule, I should say. So 1/2 times x to the negative 1/2 power. And if I make that look a little nicer, that's 1/2 times the square root of x. So there's some value, so f prime of c, there's some value c, that when I plug it into this, I get the slope of 1/3, right? The lines have to be parallel, so the slopes are the same. So I'm going to use this slide over here. No, not yet. I'm going to use that slide to do something else. But I'm going to solve this algebraically. So if I do my cross products, because we have a proportion here, 3 times 1 is 3, and this is 2 times the square root of c. Divide over the 2, you get 3/2 equals the square root of c. I don't want the square root of c, though. I want c. So squaring everything gives us 9/4. Okay, so here is our value for c. Now let me do some algebra here. That's very similar to the algebra that we did when we found equation for tangent lines. We use point slope form. All right, so when I look at my line that connects 0, 0 and 9, comma 3, you'll notice that it's going through the origin. So that line, so I'm going to say line that is 0, 0 and 9, 3, that's y equals 1/3 x. You could write this as point slope form if you wanted to, but I know that since it goes through the origin, the y-intercept is 0. So now I have the line, all right, that's tangent to this curve, right? Line at x equals 9/4 that has a slope of 1/3. All right, so to write this, I need to find the y value for this. So plug in, zoom in now, plug in 9/4. And you don't have to do all this work. I'm going to show you why I did it here in a second when I move to Desmos. So the square root of 9/4, the square root of 9 is 3, the square root of 4 is 2. So here's the y value. So my line is y minus 3/2 equals 1/3 times x minus my x value of 9/4. Anytime you want to write these as decimals, please feel free. I don't need to actually put this in a slope-intercept form. So what I'm going to do when I get to Desmos is I'm going to just show you that this line and this line obviously are parallel, right? They have the same slope, but more importantly, all right, the value in the second one that I highlighted, right, goes through the x value of 9/4. So that's the value between 0 and 9 that makes this true according to the mean value theorem. So let's go ahead and show you some decimals to help kind of put all this together in your brain, hopefully. All right, so the first thing I'm going to do is I'm going to graph that square root of x. Right now, focus on between 0 and 9, right? So 0 and 9, let's make a table so you can see those values. So I've got, let's do 0, do 1, 4, and let's do 9. Okay? Now, I'm going to also put on there the point that I found, which that value for c, all right? And that value for c was 9/4, all right? 9 divided by 4, if you want as a decimal, is 2.25, your choice. I'm going to move this one down and put on 9/4 here. All right, and again, we found the y value is 3/2, which is 1.5. All right, and that's right, where is that? Right there. All right, take that one away. Right there. So when I draw the line that connects my endpoints, 0, 0, and 9, 3, so these points here, 0, 0, and 9, 3, I'm about to draw that line. Ready? Y equals, well, let's just do 1/3 x. Get the x out there. All right, so there's the line that connects them. Now, when I draw the tangent line to this curve at the x value of 9/4, which is 2.25, it should be parallel to that black line I just drew. All right, so ready? Here is y minus 3/2 equals 1/3 times x minus 9/4. Again, that's that algebra that I just did. I'm going to change the color so there's not so much red here. Let's do blue. Okay, so now when you look at this, right, the red one, remember the red curve is our original function. The black line and the blue line, those are the parallel lines. So this blue line is called the tangent line to this curve at the x value of 2.25 or 9/4. And this black line is what we call the secant line that connects the endpoints 0, 0, and 9, 3. You'll notice those lines are parallel. That is using the mean value theorem. Okay, one more problem, one more application of this that we're going to do that has to do with velocity. Okay, so you'll notice I got a couple of slides here for this one. I got one to the right and then part C down here. So we have a rock is dropped from a height of 100 feet. Its position t seconds after it is dropped until it hits the ground is given by this position function. So you know we're going to be doing velocity. So you know at some point we're going to be having to take the derivative of this position function, right? The derivative of the position function will give you the velocity function. But before we do that, it asks us to do a couple of things that you would have learned in, or one thing you learned in Algebra 2, and then something that we learned at the beginning of this class in calculus in our chapter on limits and the beginning of derivatives with instantaneous and average velocity. So all that's going to kind of come together in this problem. So it says, determine how long it takes before the rock hits the ground. So that means I'm looking at where this, change back to my pen, right, where this position function of negative 16 t squared plus 100 hitting the ground would be a position of 0 feet. So solving this, negative 16 t squared equals negative 100. Dividing both sides, you get 100 over 16. Please, please, please feel free to reduce that if you would like. But if I take the square root of both sides, all right, I get plus or minus 10/4, which is the same as 5/2, which is 2.5. All right, now you'll notice I didn't care about the plus or minus here because I can't have negative time. So in 2.5 seconds, the rock is going to hit the ground. Okay, and that is very much an algebra type question. Okay, now let's move into something we talked about in the beginning or earlier on in this calculus class. It says, find the average velocity of the rock for when the rock is released and the rock hits the ground. So we know that the rock is going to be going from 100 feet to 0 feet in 2.5 seconds. So if I take the change in the distance and divide that by the change in time, that will give me the average velocity for this rock over this 2.5 seconds. So the average velocity is going to be the change in the distance, which is going to be S of 2.5. So plugging in T of 2.5, right? That's the last T value we have, minus the first T value we have, which is 0 seconds. It hasn't been dropped yet, over the change in time, which is 2.5 seconds minus 0 seconds. Again, something we've done in previous classes here. Now, if I evaluate this function, this position function at 2.5, you already know that that's when it's on the ground. So that's 0 feet. Minus if I were to evaluate this position function at 0 seconds, it hasn't been dropped yet. So that's minus 100 feet all over 2.5 seconds. So dividing 100 divided by 2.5, you can go to Desmos if you want for this. I'm just going to use my cell phone since it's right here. Gives me negative 40. All right, and that's feet per second. So that's the average velocity of the rock, all right, over the time frame 0 seconds to 2.5 seconds. Okay, now, what the application of mean value theorem and velocity means here, all right, is that we're going to figure out, all right, we're going to figure out the instantaneous velocity of the rock, all right, at some point must equal that average velocity. So let me actually go to the textbook here and show you something that will kind of help you right here. Okay, so I'll zoom in a little bit, not too much. It says, one application that helps illustrate the mean value theorem involves velocity. For example, suppose we drive a car for 1 hour down a straight road with an average velocity of 45 miles an hour. So if any of you are drivers out there, you're looking at your speedometer and your average velocity for that hour is 45 miles an hour. It doesn't mean that you were driving 45 miles an hour the entire time, okay? But what the mean value theorem states is that because this function is differentiable and continuous over that hour of time, that your average velocity of 45 miles an hour, right, at some point, the instantaneous velocity of the car, so when I'm looking at my speedometer on my dashboard, at some point, whenever, I don't know when it was, but at some point, we actually get 45 miles per hour on the speedometer, okay? So that's essentially what we're doing in this problem with this rock, is we're trying to figure out if we just found that the average velocity of the rock over the time frame, 0 to 2.5 seconds that it's falling, is negative 40 feet per second. At some point, if I pause that rock, which I cannot, right? If I just take my mind and pause the rock, at some point between 0 and 2.5 seconds, there's a time t where the rock's instantaneous velocity, so at that moment in time, is equal to negative 40 feet per second. All right, that's what we're going to find out. Okay? So here's what I'm going to do. You guys know that we're going to find the velocity function, which is the derivative of the time function. So this is the velocity function. So dt of negative 16t squared plus 100, right? That's going to be equal to negative 32t, all right? And so it's some value, all right, for t. So let's do the velocity at this t value, right? Negative 32 times that t must be equal to the same as the average velocity, which is negative 40 feet per second. So if I solve for that t, that's going to be the time at which the instantaneous velocity of the rock is the same as the average velocity of the rock over that entire time period. All right, so if I divide this negative 40 divided by negative 32, I get 40 over 32. We can divide both of these, let's see, by 8. And you get 5/4, which is 1.25 seconds. So essentially I'm saying at 1.25 seconds, the rock is going to be exactly that same average velocity of negative 40 feet per second. Okay? Now, let me do a little, do a little algebra here. So this actually is done. You don't need to do any more work, right? This is the time. But I want to show you when I sketch this, I'll sketch it first, of what this mean value theorem is stating. Okay, so here's the sketch. Let me go ahead and take those away. So we have negative 16x squared plus 100. And we know we're looking at between 0 and 2.5 seconds. We have 0 seconds. Let's go with 1 second. We know we care about 1.25 seconds, but 2 seconds and 2.5 seconds. All right, so I zoomed in, move this over a little bit. All right. So now you'll notice here's where the rock started. And then in 2.5 seconds, it hits the ground. All right. I put some other points here, 1 and 2. But the one that we care about is this point here, 1.25 seconds. Because at that moment, all right, 1.25 seconds after the rock has been falling, if I pause the rock in midair, the instantaneous velocity of that rock is negative 40 feet per second. And the average velocity of this rock over the entire time period is also negative 40 feet per second. So they're the same. Now let me show you what that means in terms of the lines. So if I were to connect the line between 0, 100 and 2.5, 0, you get y equals, all right, my slope is going to be the change in y. So 100 over 0, which is 100, over the change in x, which is negative 2.5. So 100 over, let me put the negative up front. I know I could make this a little nicer at negative 40. X, but you'll notice we need to go through the y-intercept of 100, so plus 100. So there's the line that connects my endpoints. All right? So what I'm saying is when I find the tangent line to this curve at x is 1.25 seconds, it's going to be parallel to this line, which we call the secant line, that connects these endpoints. All right, so watch how I do that. So y minus, the y value is 75 for that t value of 1.25 equals, I know the slope is negative 40, or I could say negative 100 over 2.5 times x minus 1.25. All right, so you'll notice there it is. It's tangent at that point. My red line, which is my tangent line, my black line, which is my secant line, those are parallel lines. And I proved all of this using the mean value theorem. Okay, now before I finish up, there's one more thing I want to show you. I'm not that concerned about it, so just take a quick read of this in the textbook if you want. But there are 3 kind of corollaries of this. And again, Calculus for Dummies will help you with this stuff. But the first one says if your function is differentiable over the interval I, so just between some numbers, and if your function has a derivative that's equal to 0 for all of these values in this interval, then the original function must be equal to a constant. Because you guys know the derivative of a constant is 0. Here's the other one, or another one. Number 2 says if f and g are differentiable over an interval I and the derivatives are the same, all right, for all the values of x in this interval, then the difference between the f of x function and the g of x function is just some value c, a constant. I'll show you graphically if you want real quick on that one. The one that I did that I thought was the most straightforward was if you have f of x is x squared, and then g of x is, it doesn't matter what the letters, but x squared plus 4, right? You notice that they are, let me zoom in on them. Let me do this, make one a table, and then it'll be nice. There we go. Okay, so if I zoom, and you can see the green and the blue here, you'll notice that the only difference is one has been shifted up or down, right? So that plus the constant or minus the constant. And if I take the derivative of this, it's 2x. And the derivative of this one is also 2x. So that's what corollary number 2 is saying. And the last one, number 3, states that if you have your function is continuous and differentiable, like we've talked about, if the derivative in between certain values in this interval is positive, then the original function is increasing. And if the derivative is negative or less than 0, then the original function is decreasing. This is stuff that we kind of talked about a little bit when we try to graph derivatives from the original function. Okay? All right, so hopefully you can take a look at this and help you out with the material in section 4.4.